Okay, hi. Yeah, so it's been a while since I recorded anything, and there has been stuff going on. So yeah, let's start with countable sets and uncountability. Yeah. So a set is infinite. I hope you can hear me. A set is infinite if it's not finite, right? And it's countably infinite if there exists a bijection f a to z plus, and conversely, if there exists a bijection z plus to a, same thing. With, with both of these, it's countably infinite. Now, just like finite sets, we have equivalence criteria, right? Oh yeah, before I will cover the proof of Z plus cross Z plus being countably infinite in the exercises. Yeah, so there's an equivalence criteria. One is B is countably infinite. So the following are equivalent, countable. Uh, Countable, it basically means countably infinite and finite. Yeah. Uh, Second is there exists the f that's surjective from z plus to b, and three there exists g that's injective from b to z plus. Yeah, so that's the equivalence criteria. So let's try proving this. And the proof is identical to what? It's identical to the finite set case. Yeah, we just have to do basically the same proof. And I'm cheating. Yeah. Hang on, now yeah. So if it's countably infinite, there's a bijective correspondence and a bijection is a surjection, so we're done, right? And if you take the other definition, then just take the inverse function. So if it's finite, then define h from a to sorry, yeah, z plus to b as follows. Uh, yeah, h of I is equal to, well, this is finite, right? So there's going to be a bijective correspondence with a finite section, right? So I'm assuming its cardinality is n because if any set is finite, it's going to have a cardinality that's equal to a natural number. Now, from all the proofs. Now, yeah, so define h of I, which to be, well, I'm going to call this g, g of I, right? And that's going to be a member of B, a unique member of B. You won't get it from another I if I is less than equal to n, and h of I is equal to 1 otherwise. And you'll get a surjective function this way. So for 2 implies 3, you'll have to use the same trick. So yeah, let's see. So we have a surjective function from z plus to b. Now we need an injective function. So for every member of B, take the set f inverse of B, right? And it's non-empty because of surjectivity. And we take, so since it's z plus, and by the well ordering principle, in z plus we have a leaf member for any subset. We can take this set's leaf member and call it g of b, right? So because this is non-empty for all b, we're going to get a member for all b, and it's going to be a unique member because the smallest number is always unique in any ordered set. So what does that mean? That means we got a function because it's the rule of assignment from b to z plus, and it's injective because if this has a common member. So if B and B prime both give the same output here, then the inverse images intersect, and that's only possible if they're equal. Otherwise, the function won't be a rule of assignment. The function f won't be a rule of assignment. And that's the contradiction. So because of that, g has to be injective. So yeah, uh, g is an injective function from b to z plus. Right. For the last one, we need the principle of inductive definition. So that's the new topic which will be covered in the next section. Yeah. So we have an injective function from b to z plus, right? Now we want to show that it's a bijection. We have a bijection, right? So if b is finite, that's pretty easy because how do we get a bijection? Let's see. No, wait, that's not the. Yeah, if b is finite, we're done because b is just by definition countable. If b is countably infinite, so not finite, then how do we handle it, right? Okay, so let's see. I'm going to cheat. Yeah, I was going about it a slightly wrong way. So yeah, we're proving 3 implies 1. So there exists an injective function from b to z plus, and that implies b is countable, right? Now we'll get a bijective correspondence by simply limiting to the range of z plus, right? So for any injective function, there exists a surjective function if you just limit the range. Now, because of that, we've gotten a bijective correspondence with some C that's going to be a subset of Z plus, right? Now, if we show that this C is countably infinite, then we're done because, or countable, because then, yeah, if this is so if B is finite, then what do we have? We have, yeah, it's countable by definition. Again, nothing, it's trivial. If B is countably infinite, we have a bijection with C that's a subset of Z plus, and we have to show that this C is countably infinite, right? So we have to show that any infinite subset of Z plus is countably infinite. And for that, we need the principle of recursive definition. Many ways of stating it. Yeah. So simply, so to show it's countably infinite, we need a bijective correspondence, and we can define it as follows. H of 1 is equal to the least member of C. Yeah, and it's a subset of Z plus, so that exists, least. And H of I is equal to least member of C minus H restricted to range of range of H restricted to all numbers less than I. So yeah, and we're defining a new function this way, and the reason this works out is going to be explained later. So, but the point is because we're using least here, it's going to be a unique number, and therefore, and we have to show this is surjective now. Why is this surjective? Well, yeah, you pick a C in C, right? And you have to show it's covered by some edge. Injectivity is, I believe, trivial because, yeah, h of if they're not equal, one of them is less than the other, and by definition, it's not in this set. So we're done that way. Now for surjectivity, yeah, let's see. I'm keeping. Yeah, okay. So h is a function from z plus to c. Now, since c isn't finite, we're given that it's not contained in any uh, it's not contained in any section. H of z plus is not contained in a section of integers, right? This is because it will contradict the corollary of finite set, because then we'll have an injective function from z plus to that. Yeah, okay, so let's show that C is surjective. This function is surjective. Yeah, let's show that C is surjective. Okay, sorry, I just worked on it a bit. Okay, so take any arbitrary C and Z, right? Now, okay, first of all, H of Z plus is not going to be contained in any section of the integers, right? That's because Z plus is infinite. So that would imply Z plus is finite. So if this containment were to be the case, so that's a problem. Now, because of that, well, every C will occur at least once. So yeah, so for every C and C, there exists n in Z plus such that h of n is greater than C, right? And you take the set of all such n and you take the least, right? So let's call that h of m. So that's greater than equal to C by definition, right? Now, since it's the least member that doesn't that's greater than C, the h of, let's say, the section till m minus 1 is going to be consisting of members that are less than C, right? So what does that mean? That means, yeah, C is not going to be contained in this range. And since C is the smallest member, that must be, so h of m is defined to be the smallest member of C that is not including this, essentially this. Yeah. And C is, so C is greater than that. So h of m could either be contained here or equal to that. But it definitely can't exceed it because C is definitely an example of a element of C that's not contained in this, but contained in C. So what does that mean? That means h of m is less than equal to C, right? And that implies h of m is equal to C. So there exists an m in that plus that such that h of m is equal to C, right? To summarize, there exists some integer that's greater than C because it's not finite, z plus. And because of that, we have the least member and that's greater than equal to C, and the least member will also be less than equal to C because its previous section will be contained in all in essentially S of C, which I'll define later. It's the section this. That's the definition of a section in general. I'm just using it right now. So yeah, that's how you prove it. And the justification of this function, the existence of this function uses the principle of recursive definition. Okay, now let's prove some theorems. Yeah. Okay, a subset of a countable set is countable. So an infinite subset of a countable set because so yeah, we just use the bijection stuff. So it follows on the corollary, basically. Yeah, I'll just take it precisely. Yeah, there's an injection from FA to Z plus. Simply, so there's a bijection from B to Z plus, and there's an injection from A to B since it's a subset, and you use that to define the subset from A to Z plus. So you're done. And Z plus cross Z plus, there's another proof that it's countably infinite, and that is, yeah, so we have an injection from this set to Z plus, and that comes from the fact that there are like the primes don't intersect with each other actually. So we define m comma n as 2 to the power m times 3 to the power n, right? So how do you show it's an injective function? That really matters, right? So if m is so if n are equal and m isn't, yeah, if both, okay, so 2 to the power m prime dot 3 to the power n prime is equal to 2 to the power m dot 3 to the power n, right? Now, yeah, sorry, not equals. We have to show this given m comma n is not equal to m prime comma n prime. All right, so this can happen only if either m is not equal to m or m n is not equal to n prime, right? If both of them are equal, yeah, if both of them are equal, then the set happens to be equal. So that's the problem. So we can take both of either of them to be equal, right? So I'm taking three cases, one where one of them is equal and one where both of them aren't equal, right? If one of them is equal, then we can just cancel them because the powers are unique, right? And from the inequality, essentially, you can use the inverse law we've proven to show e to the power n minus n is not equal to 1. And that's because this is not going to be equal to 0, right? So that's what happens when one of them is equal. Now, in the case where both of them are unequal, how do we show the primes aren't bothering each other? Ah, yes, you use the parity. So, okay, yeah, you just divide it by 2 to the power m on both sides. And since this is an even number, given that they're not equal, so it's not going to be 1. This will be an even number and this will be an odd number if they're equal. So that's a contradiction. So we're done. Okay. Yeah, similar proof for Q plus because Q plus is there's a bijection with that Q plus and Z plus cross Z plus. Yeah. Okay. This proof is wrong, but we'll discuss the incorrect uh, usage later. Okay. A countable union of countable sets is countable. All right. So essentially, okay. Yeah. So we have a countable collection of uh, countable sets. So let's call that AN. That's given to us, right? That's how we define a collection, right? Cartesian product, almost the same thing. Yeah. Now, given that, okay, so now what? Yes, this is the mistake I'm already telling you right now, but because each of these are countable, for every AN, there's a bijection Fn or a surjection if you want from AN to Z plus, right? Yeah, yeah. So for each AN, there's a surjection for every N essentially. There's a surjection from AN to Z plus, right? And since this is indexed by integers, there's a surjection from, actually, I'm going to call it J here. Yeah. And this J is either finite or Z plus. Yeah. So there's a surjection from Z plus to J. So what does that mean? Well, it's countable, right? Yeah. That was my bad. Yeah. Okay. So because of that, we have, so for each j, we have an fn, right? Because they're indexed by this set j. So from this, we can get a function from z plus cross z plus to z plus and define it as what? As, yeah. Or is it that? No, it's, we'll have to, yeah, to union of A. So I'm going to call union of A is essentially the collection of all the members of AN, each AN, right? Yeah. So uh, H. Yeah. So the surjection here is defined as H of K comma M is equal to F of G of K M. So this M is here and this K is here, right? So we're choosing which N to use. And this is going to belong to A prime. And this is a surjective function. Yeah. Why is it a surjective function? Because, well, this is a surjective function and this is a surjective function. So because an indexing set is always surjective, right? So by composition of surjective functions, this is surjective. Yeah. What else? Yeah, so the mistake is here and I'll discuss this later. Okay, a finite product of countable sets is countable, and for that we use a similar approach. Yeah, so given that Z plus cross Z plus is countable, we can show that A cross B is countable by just defining the surjective map MGN, comma N using the same maps. So yeah, the book completely covers it. And then we just use induction. So that's how we get the finite case, right? So we just break it down and then we multiply it with a new one. And by since this will help us with the inductive step essentially, and there's nothing wrong with this. But for the countable union, we can't use it for every single integer. That's the point. A finite union of countable set is actually countable. That's not a problem. Yeah. Okay. Uh, yeah. X to the power omega, which is the set of all functions from X, which is this set. Sorry, all the functions from omega to this set is uncountable, right? And the point is, if there exists a bijection from z plus to x omega, then we can choose a new one. You from this bijection that intersects with none of them, and that's the diagonalization argument. And you can see this in the profile. There's a video about it. It's a very popular one. Essentially, you just switch it at every single one, right? And since there's a bijection from x to the power omega and omega to the power omega, right? And therefore, there's also a bijection from 0 to 9 to the power omega, right? Because it's in between 2 and infinity, count, the countable infinity. So because of that, you can change the digits, even if you want it this way. So all decimal expansions are also uncountable by the diagonalization. And the more general version is attached in the next one. So I'll discuss that now. Yeah, this is, so because 2 to the power omega fine x has a bijective correspondence with x power set of omega, fine uh, essentially the proof can be used. The proof for the general case, which the book covers, can be used for extra parameter. Okay. So yeah. So if we have an injective map G from power set of A to A, we automatically get a surjective map from A to the power set of A because okay, yeah. So we just have G inverse of A for any A, right? And because it's injective, it's going to be a unique value, and we can define that to be H of A, right? And we can define it arbitrarily on the rest. So that's a surjective map from A to power set of A, right? So if we have an injective map, it implies there's a surjective map. So all we have to show is that there is no surjective. So we have to show that there is no surjective map from A to power set of A, right? And if so in the x to the power omega example, we switch the value of one at all the right ones, right? Uh, so at a diagonal at every point. And that's exactly what we're going to do here, except the ones and zeros here are the characteristic functions, right? So that's why we're tackling the set B, which is going to be a subset of A. So it's going to belong in the power set of A, and therefore definitely must be in the output in the range. Otherwise, G won't be surjective, right? So we're defining a subset of B based on G, and we're going to show that it's not going to lie. So B is equal to A. A belongs to A minus G of A, right? So G of A is going to give rise to a set, and because of that, we're flipping it. It's the members which don't belong there, right? A minus G of A, that's just we're switching the set out. And this set will not belong to the range of this function no matter what because of this trick. It's the same flipping of ones and zeros, but extended to the set theoretic notation. So let G of A naught is equal to B, right? Because it's supposed to be surjective, right? So A naught belongs to B uh, if and only if A naught belongs to A minus G of A naught if and only if A naught belongs to A minus B, which means if and only if A naught well, belongs to A, which it does, and A naught doesn't belong to B. So it's a contradiction. Yeah. Okay, so what does that mean? Yep. Yeah, so that's the complete theory portion. Let's go to the exercises now.